Hello, my name's Cameron. The title of this work is A Tolerant Independent Set Tester. So let's start with the independent set problem. So given a graph on n vertices, does it have an independent set of size rho n, where rho we can think of as some constant? And recall that an independent set is a set of vertices such that no two vertices are adjacent. So in this graph, I've circled an independent set of size 3. So this is one of the classic NP-complete problems, so it's believed to be hard to solve. And in fact, it's even hard to approximate this problem. But it turns out there's a property testing version of this problem that is easy to solve. So in this version of the problem, we want to make it a little easier. So now we just want to distinguish between the cases that the graph has a independent set of size rho n and the case that every subgraph on rho n vertices has at least epsilon n squared edges. And for graphs that don't fit into one of these two categories, we don't worry about those inputs. And Goldreich, Goldwasser, and Ron introduced this notion of property testing and this problem in the 90s. And what they showed was that with high probability, you can distinguish between these two cases by just inspecting a random subgraph on rho over epsilon to the 4 vertices. So this is kind of surprising because we know the standard independent set problem is very hard to solve. But in this problem, if rho and epsilon are constants, then you can solve this problem by looking at only a constant number of vertices. And I'll note that whenever I have this tilde, I'm hiding logarithmic factors in epsilon and rho, but there's not in n. So let's add some definitions to this. So we'll say an epsilon tester for the rho n independent set property is an algorithm that takes a random sample of S vertices, looks at the induced subgraph, and can distinguish between these two cases. And we'll call the second case the epsilon far case. And S, so the number of vertices, is called the sample complexity of the tester. So ideally, we want the sample complexity to be as small as possible. And so now, rewritten using these definitions, the Goldreich, Goldwasser, and Ron theorem says that there exists an epsilon tester for the rho n independent set property with sample complexity rho over epsilon to the 4. So in some prior work with Eric Blay, we showed that we can actually improve this bound. So we gave an epsilon tester for the rho n independent set property with sample complexity rho cubed over epsilon squared. And this is tight up to logarithmic factors because there's actually a lower bound by Feige, Langberg, and Schechman of this same sample complexity. So for this property testing version of this problem, it seems like the bounds are quite well understood. But there's kind of a weakness with this standard notion of testing. So again, these are these two cases we're trying to distinguish between. But suppose we had an input graph like this, where imagine it's like a very dense graph, or maybe even a complete graph, and take a set of vertices of size rho n and put an independent set, and then maybe add like one edge. And the problem is these property testing algorithms have no guarantee on this type of input because they don't fit into either of the two cases. But ideally, we would maybe want the algorithm to accept this type of graph. Perhaps there was some noise, it was a yes instance and there was some noise added, or perhaps the sampling made some mistakes. And so ideally, we want this to be like a yes instance. And this motivates the notion of tolerant testing. So this was introduced by Parnas, Ron, and Rubenfeld, and they introduced this for any property testing problem, but we're just going to focus on the independent set property. So now we're going to have an epsilon 1 and epsilon 2, and we want to distinguish between the cases that the graph has an induced subgraph on rho n vertices with less than epsilon 1 times n squared edges. So this is like an epsilon 1 close case, and the epsilon 2 far case, which is the same as before. So again, we can picture the yes case as like there's some sparse subgraph, and the no case says that every subgraph is sufficiently dense. And an algorithm that can distinguish between these two cases with high probability is called an epsilon 1, epsilon 2 tester. So here's the definition again. And just a few remarks. First, it's worth noting that this does in fact generalize the standard uh, testing problem. So if we plug epsilon 1 equals 0 into this, we get the standard testing problem out. But in general, epsilon 1 may be a function of epsilon 2. And we're interested in when is tolerant testing harder than the standard testing problem. And it turns out in some cases, when epsilon 1 is roughly on the order of epsilon 2, there can be an exponential gap between the query complexity of the standard testing problem and the tolerant testing problem. So what about the independent set property? Is there this gap between the tolerant testing and the standard testing? And what we show is that this is not the case, that there's a tolerant tester where epsilon 1 is roughly on the order of epsilon 2 for the rho n independent set property with sample complexity rho cubed over epsilon squared. And so this sample complexity bound matches the bound for the standard testing problem up to logarithmic factors. And in fact, it generalizes the container method approach that was seen in the prior work. And we'll note that this also improves on the best prior bounds for tolerant testing of the rho n independent set property. So it was not studied directly, but there are a number of results for testing general graph partition properties. And it's been shown that you can tolerantly test general graph partition properties, but with a polynomial dependence in epsilon that is quite large. And so we improve on that. Okay, so here's the plan for the rest of the talk. I want to introduce our main technique, which is this graph container method, and go over the rough idea of how this can be used to prove testing results, which was seen in the prior work. And then I'm going to discuss our new graph container lemma and describe some of the ideas behind this proof. And I'll also discuss one other application of our new container lemma. Okay, so what is the container method? The container method is a tool for characterizing independent sets in some graphs. So for example, if we look at this graph, there are lots of independent sets in this graph. So if you count them, there's roughly like 15 independent sets. I've just circled 3 here. But it turns out you can find a set of containers where each container is a subset of vertices such that all the independent sets are contained. In other words, they're a subset of each of these containers. So for example, in this graph, there's lots of independent sets, but I can give you these 3 containers, for which every independent set is a subset of one of these containers. And the important thing to note is number 1, there's not too many of them, because I could just give you all the possible subsets of the graph, and that's not very interesting. And 2, they're not too large, because again, I could just give you the entire vertex set as a container, and that's not very interesting either. So a little bit more formally, the first time this container method was used was by Kleitman and Winston, although they didn't phrase it like this, but this is roughly what they showed. So if a graph is epsilon far from having a rho n independent set, then there exists a collection of containers where we use this collection is going to be a subset of the power set, which we denote by 2 to the power of v. So each container is a subset of vertices, and the collection is a subset of the power set that satisfies these 3 properties. Number 1, the collection is not too large, so there's not too many containers. Number 2, each container is not too large. And importantly, for every independent set, there is some container such that the independent set is a subset of the container. So this type of container lemma has seen a number of applications in combinatorics, and the main reason being is that this was generalized to the hypergraph container method, and it turns out that a lot of problems can be mapped into problems about independent sets in hypergraphs. And then you can use these hypergraph container lemmas to do lots of different things on the objects. So if you're interested in some of in more of the applications, I'd recommend these two surveys. But for now, we're just going to focus on these basic graph container lemmas. Okay, so now I want to discuss how can we use a container lemma to prove a testing result. So now suppose we're going back to the standard testing problem where we want to distinguish between graphs that have a large independent set and graphs that are far from having a large independent set. So what's the first algorithm that comes to mind? You're just going to take a random sample of vertices and check if the induced subgraph on that sample of vertices has a large independent set. So an independent set of size rho s. And it's not hard to show that in the yes case, your random sample, you should find a reasonable number of vertices from the independent set. And so it will accept, which is what we want. So that's good. And the hard case is on these no instances. So we want to show that if G is epsilon far from having a rho n independent set, then S contains a rho s independent set with only some small probability. So again, this is the challenge here. So a naive approach might be, we know that for S to have an independent set, it must come from some independent set, larger independent set in the graph potentially. And so we can take a union bound over all the possible independent sets in the graph and say, what's the probability you find rho S vertices from that independent set in your sample? And now the problem is that there may be too many independent sets in the graph. So this union bound just won't work. So how can we use a container lemma? The key point is using that container lemma, any independent set is contained in a container. So what that means is that for our sample to find a rho S independent set, it must find rho S vertices from at least one of these containers. So now we can union bound over this relatively small number of containers. And since each container is fairly small, then we can upper bound the probability that we get a lot of vertices from that container. So this was the main approach used in the prior work, but I'll note that they didn't actually use this original lemma by Kleitman and Winston. In order to get the tight bounds, they had to prove a stronger container lemma, which I won't go into the details of. But this is at a high level the approach. Okay, so now how could we generalize this approach to tolerant testing? So again, now we want to distinguish between the case, well, the yes case is going to um, be a graph that has a set of rho n vertices with a relatively small number of edges. And the no case is the same as before, being epsilon far. So again, what's the first algorithm that comes to mind? Take a random sample of vertices, and this time check if the induced subgraph uh, has a set of vertices with a small number of edges. So before we were checking to see if the sample has a large independent set. This time we're checking if it has a large sparse set. And again, the yes case, it's not too hard to show that if you take a sample, you should find a relatively high number of vertices from this original sparse set in the graph. And so these should be relatively sparse. Now, the hard case is again in this no case. And this time we want to show that if our graph is epsilon far from having a rho n independent set, then we want to show that the sample finds a not only does it not find an independent set, but it doesn't find a sparse set. Or in other words, it finds a sparse set with only small probability. And again, here I'm using the phrasing sparse set to mean that the induced subgraph has a small number of edges. Okay, so what would be the desired container lemma that we'd like to prove? So we'd like to show that if our graph is epsilon far from having a rho n independent set, then again, there's a collection of containers. These first two things are the exact same, small number of containers, containers are relatively small, and this is the only change. Now we have that for every sparse set, we want a container such that the sparse set is fully contained in the container. So this is what we would hope for. But it turns out um, having this containment is not possible. And we'll give a few more details on this later on. And in fact, there's been no prior results of this form. The only similar type of results were applied to subgraphs that had either a much smaller density than this, or they had some bound on the maximum degree. But there was no results where that applied for sparse subgraphs of up to this density. So here's the lemma that we prove, up to some small details that I'm omitting. So again, it starts as the same. Let G be a graph that's epsilon far from having a row n independent set. Then there's a collection of containers such that the collection is small, the containers are small. And this time, we're going to have, for each sparse subgraph, there is a container and some alpha, such that the sparse set is mostly contained in the container. So what I mean by that is that the intersection of this J and that container is relatively large compared to J. And so informally, you can think of this as each sparse set is mostly contained in a container, whereas before we had that each independent set was fully contained in a container. And then using this new container lemma instead of the standard container lemma, we can prove the theorem on tolerant testing. So I won't go into the details of that. Okay, so now I want to give some of the details on how we go about proving these container lemmas. And to start, I'm going to describe how we do it for independent sets, which will set up what we have to change for sparse subgraphs. So I think the best way to introduce this is through an encoding argument. So suppose we have some graph, and I'm thinking about an independent set in this graph. So we can both see the graph, but only I can see this independent set. And suppose I want to tell you about my independent set in the graph, but I don't have time to tell you all the vertices. So I can only tell you one of the vertices in my independent set. And I want to tell you the most information about it as possible. What can I do? So if you think about it for a minute, you might think, well, I can only send you one vertices. Maybe I can send you the highest degree vertex in my independent set. Now, why is that useful? If I tell you this vertex, you can immediately rule out all of the neighbors of that vertex from being in the independent set. So this is great. I've told you one vertex and you've ruled out these four vertices. But there's actually more you can say. Because I've told you this is my highest degree vertex, any vertex with higher degree cannot be in the independent set. Otherwise, that's what I would have sent. So these two vertices here have degree higher than the vertex I sent. So in fact, you can rule those out as well. So surprisingly, I've just told you one vertex from my independent set, and you figured out exactly what my independent set is. Now, more generally, we may want to repeat this process. The graph may be much larger, and so what we can do is just repeat this in a greedy fashion. So I've written out the algorithm here, but it's basically the same thing of what I just said. So pictorially, what will this look like? We have some graph and some independent set that I'm trying to tell you about. So what can I do? I can tell you one vertex, and we're going to call this the fingerprint. What I tell you about these vertices I sent, we're going to call the fingerprint. So I can tell you this vertex, and you can immediately rule out a bunch of vertices and get what we're going to call a container for the independent set. And then we can repeat it. So I can tell you another fingerprint vertex, and you can reduce the container even further. And we can just keep repeating this until we're happy with the size of the container. And at the end of this, we're going to call the vertices I sent the fingerprint of the independent set, and we'll call the container the container of the independent set. And there's a few important notes here. So first, because of what we were saying before, at no point will a vertex in the independent set be removed from the container, because we're only removing neighbors and higher degree vertices. And so we have that the independent set is a subset of the container. And further, maybe a little more surprising, is that the container of the independent set is exactly equal to the container of the fingerprint. And really what this means is, like, if I just gave you the fingerprint, you could reconstruct the container. That's the main punchline, is you don't actually need the independent set to construct the container. So how can we use this idea to prove a container lemma? So again, this is the container lemma by Kleitman and Winston. So the big question is, how do we construct the collection of containers? And maybe surprisingly is all we're going to do is we're going to let the collection of containers be this, we're going to run this procedure on every single independent set in the graph. And you might be thinking, well, this collection is going to be very large because there's a lot of independent sets. But here's the key point that we saw before, is that the container function, you can reconstruct it just from the fingerprint. So really, this set of containers for every independent set is really just the set of containers of all the fingerprints. And which again, we can rewrite it like this. So really, it's just the containers on all fingerprints. And because these fingerprints are small, there's only so many possible containers. And that's the main punchline. That's how we get this bound of there's at most n choose 1 over epsilon containers. It's because our fingerprints are going to be of size roughly 1 over epsilon. And so there's only n choose 1 over epsilon possible ways you could make a fingerprint. So I won't go into more details. In order to prove this lemma, you also have to show that the containers are small. But this is, again, the rough idea of how you construct this collection of containers and why this containment properties hold. Okay, so how can we generalize this for sparse sets? Just first, I want to restate this new lemma that we prove. So again, what we're going to show is that if G is a graph that's epsilon far, then there's a collection of containers such that the collection is small, the containers are small, and the sparse sets are mostly contained in these containers. Again, omitting some details here. So let's go back to this encoding idea. So before, recall that there was an independent set, and I was trying to tell you about this independent set by sending one vertex. But now this time, let's pretend we have a sparse set. So let's consider the set J. So I'm thinking about this set J, for which there's not too many edges, and I'm going to try to tell you about this set by telling you only a small number of vertices. And remember, this time the goal has changed. We're not trying to get full containment in these containers. We're just trying to get that the set is mostly contained. So what can I do? And this time it's a little trickier because remember before I just sent the highest degree vertex. But the problem is if I tell you this vertex and you try to remove the neighbors, you may accidentally remove a lot of the sparse subgraph. So you don't want to do that. So what can we do instead? So what we end up doing is actually we're going to split these two operations. Before we had this operation of that I would send you a vertex and then you remove the higher degree vertices and remove the neighbors. And this time we're going to split these two operations. So what I can do is send you a vertex and I will tell you remove the higher degree vertices. So for example, I can send this purple vertex and all the higher degree vertices you can remove. And so unfortunately, we did actually remove one vertex from the sparse set, but we did also remove all these other vertices on the outside. So we're going to consider this a win. And then we can again repeat this process. This time I might send you the yellow vertex and tell you to remove the neighbors. And so doing that, you'll remove these two other vertices. So what's happened here? This time, instead of sending one vertex, I've sent you two vertices as well as a bit for each vertex to tell you which operation to do. And using that, you can remove all these vertices and figure out that my independent set um, is is mostly contained in what's left, which is just these three vertices. So again, we can repeat this type of argument. I've written out the algorithm here, but roughly it's the same type of thing where we just want to repeat this. And maybe one point to note is what we're going to be repeating is we're going to pick a vertex and an operation that maximizes the ratio of the number of vertices removed from the container divided by the number of vertices removed inside J. In other words, we want to minimize the number of vertices removed from our sparse set while maximizing the number of vertices from the container that are removed. And so what would this look like if we have some sparse set J? After some number of steps, we'll have these fingerprint vertices, which I've sent, and from that, we also have a container, which may accidentally remove some of J, but hopefully it'll contain most of J. And again, we have these key observations that the container, even though we use J to construct it, it can be reconstructed just from the fingerprint. But now this time we have that J is not fully contained in the container, and really the most of the proof is about proving that there's a sufficiently large amount of J that is contained in the container. So I won't go into the details of that. For that, you'll have to check out the full paper. Okay, just to wrap up, I want to mention our original, we tried to prove this container lemma in order to prove a new tolerant testing result. But it turns out that this new container lemma has another application. So there's this famous theorem about counting independent sets in regular graphs. And what it says is if you have a d-regular graph, then the number of independent sets um, is at most this expression, roughly 2 to the n over 2. So the upper bound was proved by Zhao in 2010, and the lower bound comes from Alon proved this there's an example of roughly n over 2d copies of this complete bipartite graph, which actually matches this, uh, which shows that it is possible to reach this number of independent sets. So this is a famous theorem, and it was actually first conjectured by Alon in the 90s, and it took some time to prove this theorem. There was a number of improvements slowly over time. And one of which was this result by Sapozenko. And in that, uh, the container method was the main technique. And this is actually at the time, this was one of the classic applications of the container method. And so the question we have is, what about sparse sets in a d-regular graph? So we can upper bound the number of independent sets in a regular graph, but what about sparse sets? And now, since we have this new container lemma, for sparse sets, can we use it in place of the standard container lemma that was used by Sapozenko? And so what we show is that, yes, using this container lemma just right in place of the previous one, we can show that the number of induced subgraphs in a d-regular graph with edge density at most this expression can be upper bounded by roughly 2 to the n over 2. Now, a few remarks. You might be wondering, where is this edge density expression coming from? Why is that interesting? Well, observe that for a d-regular graph, the edge density of the graph itself is d over n. And it's not hard to show that there's actually a very large number of induced subgraphs with edge density at least roughly d over n. So, and Zhao's result says that this is the number of induced subgraphs with edge density 0. But what we show is that for edge density up to roughly some d over n divided by some polylogarithmic factor in n, there's still only roughly 2 to the n over 2 induced subgraphs. So in other words, we can have density a fair bit larger than 0 and still have a lot of induced subgraphs. And in fact, this exact same example that gave the lower bound for the independent set cases gives a lower bound here. And it illustrates that there should be some dependence on a D and K in this form. So ours is by no means tight, but it demonstrates that there should be some sort of expression that has some K and D dependence. Okay, so just to summarize, we proved this new graph container lemma for sparse subgraphs, and we used it to show a tolerant tester where epsilon 1 is roughly on the order of epsilon 2 with sample complexity, which matches the sample complexity of the best tester in the standard setting. So some basic questions are, what about a fully tolerant tester? So it's usually desirable to have epsilon 1, for this to work for any epsilon 1 and epsilon 2. And this, if you can do this, then you have things like distance approximations. But it turns out that there seems to be some challenges with using the container approach to get a fully tolerant tester. Another question is, can we use these techniques to test or perhaps tolerantly test some other graph properties like K-colorability or cut properties or general graph partition properties? And finally, we suspect there should be other applications of this new container lemma for sparse subgraphs. So we demonstrated one example where you can take this new lemma and put it in the place of the standard lemma and get some new bound, and we suspect there should be other examples. Okay, that's all. Thank you.